Hello, good evening to all of you. Am I audible?
Good evening, sir. Yes, sir.
Good evening. Good evening. Share my screen. Is my screen visible to you?
Yes, sir.
Okay, let us start with the attendance. Please answer your attendance. Aditya Kumar,
Present, sir.
Anand,
Present, sir.
Ananta Kumar,
Yes, sir.
Arnachalam,
Sir, mic issue, sir, for you.
He
Yes,
joined, sir.
message.
what is
connected
that?
and yes,
Mic is
message
not
also.
working.
Yes, sir,
He
message.
joined,
Yes, message, sir.
Okay. Hasan,
Present, sir.
Heyman,
Present, sir.
Jehan,
Yes, sir.
Kesav Prasad,
Yes, sir.
Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul, Rahul, Roshan Kumar,
Present, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Mallish,
Yes, sir.
Vigneshwaran,
Present, sir.
Jayraj,
Present, sir.
Vikas,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Present, sir.
Yuvraj, Yuvraj. Okay, so two people are absent today. One is Rahul, other one is Yuvraj. Okay, so welcome back to this course on IC engine combustion and pollution. So we are in chapter 2. We are now discussing about thermodynamics of combustion. I have introduced this chapter with the objective behind studying thermodynamic aspects of combustion. Combustion as such is complex both in SI and CI engine. In SI engine, it's flame propagation based, and in CI engine, it is mixing, air fuel mixing based combustion even. And there are several physical and chemical processes that happen, and they are coupled. So that is the complexity of this process that happens in IC engines. Okay, so considering that, we are starting with a simplified thermodynamic aspects, which is based on steady state approximation. By using this thermodynamic principles, we are deriving useful parameters about combustion event, and these parameters are helpful in better analyzing the combustion event. So we started with this stoichiometric principle, wherein we could relate reactant composition with the product composition. The objective behind this principle is to get the product composition, because some of the products are pollutants. The products I'm talking is about the product that are released due to fuel air combustion, okay, in our IC engine. So this principle help us to get composition of the product by relating the number of atoms in the reactants and products, right? Atoms, number of atoms of each element in the reactants and products are conserved. Based on that principle, we could get product composition by knowing the reactant composition. So the only information you need to know to get product composition is the molecular formula of the fuel. From that, you can get the product composition. But it's a simplified approach. You cannot get more number of products. So the number of product you can get, I mean the composition you can get, is based on the number of equations you can form, and the number of equations depend on the number of atoms in the reactant side. Okay, so we have seen that at the most we can form only 4 equations because of 4 atoms, right? Fuel and air combustion. The fuel is hydrocarbon, carbon and hydrogen are the 2 elements in the fuel. In air, oxygen and nitrogen are the 2 elements. So you have only 4 atoms on the reactant side. At the most, you can form 4 equations, meaning you can find at the most 4 components in the products. Okay, that is the limitation of this approach. After that, we discuss how we can apply first law of thermodynamics to study the combustion event. Here, I said that we could get 2 useful parameters by applying first law. One is heating value, which is an estimate of the thermal energy that is released because of the combustion event. So heating value is also property of a fuel. So that's why it is measured under control condition, and we have imposed 2 conditions to measure the heating value. Since it's a property, it should be measured under reproducible conditions. So we said that when we measure heating value, the combustion event should be complete. This is one condition, and second one, the products are cooled to initial temperature. So by imposing these conditions, we are creating reproducible condition to measure heating value in a bomb calorimeter. Okay, and we also discussed that there are 2 heating value, higher and lower heating value. Heating value is an important parameter from IC engine perspective because it helps us to define first law efficiency. First law efficiency of IC engine or thermal efficiency of IC engine is defined based on the heating value, and you know thermal efficiency is one of the important performance metric of IC engine. We use this parameter often to examine how well the engine is performing. So in the heating value that you substitute in the thermal efficiency equation, you need to use lower heating value. Higher heating value is a value when the H2O is condensed to liquid phase in the product, combustion product. This never happened in IC engine. The H2O will always be in the vapor phase, so you need to use lower heating value. But when you use an instrument like I said, bomb calorimeter, to measure the heating value, you are actually measuring higher heating value. So you need to know how to convert this higher heating value into lower heating value. This is what we have discussed in the last class. So now we know how we can do this conversion, right? This is what we have discussed. This is higher heating value on the left hand side, and the right hand side you have lower heating value plus heat that is added by recovering latent heat of vaporization. When you condense vapor into liquid, heat is liberated. Okay, this is opposite to what is happening when a liquid is converted to gas. It absorbs latent heat. When a vapor is converted to liquid, it liberates latent heat. And that latent heat, whatever liberated from H2O, is added to lower heating value. This is how you get higher heating value. So in the efficiency equation, you need to use this lower heating value. So you need to know how many moles of H2O are found in the product. This is the only information you need. To get this, you need to know the molecular formula of the fuel. So this is how we define the first law efficiency. Work extracted by burning unit mass of fuel with respect to thermal energy release by burning unit mass of fuel. Work is not measurable in IC engine context. So we use this fundamental equation and express this in terms of power. That is what is the second form of first law efficiency or thermal efficiency. Power divided by m dot f into q with a subscript c. This is what is heating value, and we need to use this lower heating value, right, as we discussed. So after this, we started our discussion on adiabatic flame temperature. This is again one of the important parameters that you need to know. This is a maximum temperature reached by the combustion product. Maximum temperature reached by the combustion product is adiabatic flame temperature. This is a theoretical or hypothetical value. Okay, then why we are interested in this theoretical or ideal value? Because when you design an engine, IC engine, you have to carefully, engine is an assembly of various components. Okay, so various components, you have to carefully choose a material to design various components. And one of the fundamental information you need to know for the choice of material or designing the engine component is the maximum temperature that is reached in the combustion system. Okay, so we always design anything with a factor of safety. Considering that, you need to know the maximum ideal temperature that can be reached in a combustion system, which help us to carefully choose a material and design the component, okay, so that the durability is high. So you know IC engine durability is 10 plus years, and one of the reason is we provide high factor of safety, and to do that you need to know all this ideal or hypothetical values, right, to choose material appropriately. So that is the usefulness of this parameter, adiabatic flame temperature. This is under adiabatic condition. You know what a adiabatic condition is. What is an adiabatic condition?
Q is equal to 0, sir. Means there is no heat transfer.
Energy exchange. Energy exchange.
Yeah, so there is no heat interaction between the system and the surrounding. When I say system, please remember that system is a fixed mass of matter. What is the matter we are talking here? We are talking about chemically reacting system. So we are talking in the combustion context. What we are talking is chemically reacting system. Chemically reacting system is a fixed mass of matter. Here the matter is fuel plus air before the start of combustion reaction. After the end of combustion reaction, what you have in the system is products, various species produced due to combustion event. This is what I mean by chemically reacting system. Whatever we are deriving now is applicable for this particular system. So when I say adiabatic system, the system doesn't interact with the surrounding. There is no exchange of heat between the system and the surrounding. Meaning in an IC engine context, you can imagine that the engine is perfectly insulated. So there is no heat interaction between this system and the surrounding. This is what I mean by adiabatic system. Okay. And you know, when you insulate the system, there is no heat loss. So the temperature reached by the product after the combustion event is going to be maximum. That's why we say that this is a maximum temperature reached by the products of combustion under adiabatic conditions, wherein there is no heat interaction between the system and surroundings. Okay, Q is 0. So we are interested to get an estimate of this adiabatic flame temperature for two reasons. One, it will help us to carefully choose the material to design the component for longer durability. Second one, this temperature value also affect the pollutant formation. Later on, I will discuss how the temperature value affect the pollutant formation. But temperature reached in the combustion system is one of the vital or critical information that is required to know how much of the pollutants are formed. For example, NOx, oxides of nitrogen, are highly sensitive to in-cylinder temperature. The maximum temperature reached in the combustion system is going to fix the maximum value of NOx that is formed in the system. So from the pollutant formation perspective, we need to know this temperature. From engine design perspective, we need to know this temperature. Okay, that is the usefulness of this parameter, and that is the reason why we are focusing on how to get an estimate of this temperature by applying first law. So now with the background information, before we see how we can derive an expression or how we can compute or estimate adiabatic flame temperature, we need to know what are the variables that influence this value, temperature value. So I need to know what are the variables that affect or influence the value, maximum value of this temperature. So this adiabatic flame temperature depends on this variable. I yesterday stopped here. One of the important variable is fuel type. Fuel type, because the type of fuel that undergoes combustion is going to fix the maximum value that is reached at the end of combustion. For example, if you combust gasoline or diesel, these are hydrocarbon fuel. They have a fixed value of carbon and hydrogen, and because of that molecular composition and molecular structure, it releases energy. So what is the energy source, thermal energy source? So when you talk about thermal energy released in combustion, what is the source for that energy?
It's basically burning of fuel, sir.
Fuel. So you can say that fuel is a source, energy source. Okay, so when I say fuel as energy, what energy we are talking here in terms of fuel energy?
Enthalpy of formation, sir.
Enthalpy of formation or chemical energy, right? Fuel as such possesses carbon with a particular molecular structure. So these are basically compounds. You know, a compound is formed from an element, okay, through bonds. So it means already some energy is spent to form a compound from an element, and that energy is what we refer it as enthalpy of formation or chemical energy. During combustion, that energy is released as a heat, and that will appear in the product temperature. So the product temperature will slowly rise because of the thermal energy release. So we can say that fuel has a strong influence on the temperature reached at the end of combustion, because fuel is what is energy source. Depending on what type of fuel you are burning, the temperature reached during the combustion is dependent on. For example, if you burn diesel, you are going to get one temperature. If you burn alternative fuel like ethanol, as I said, it's used in US along with gasoline. So if you burn those kind of fuel, you are going to get different temperature, because the molecular composition and molecular structure of those fuels are different from hydrocarbon fuel. Fuel is one of the important. This is what we are referring it as adiabatic flame temperature. The second variable here is initial temperature and pressure of the system. Again, system is a fixed mass of matter. Depending on the initial conditions of the system, initial temperature and pressure, the final temperature reached at the end of combustion is going to be dependent on. For example, if you look at engine context, fuel and air, if it you provide any intake before it is sent into the engine cylinder, it's going to increase the final temperature. Similarly, pressure. Pressure can be ambient pressure. If you use a turbocharger or supercharger, you're going to increase the initial pressure. Once you increase initial pressure, the final flame temperature is also going to be higher. So we can say that based on the conditions, initial conditions, temperature and pressure conditions, the flame temperature, maximum flame temperature is going to be different. Third one is fuel or equivalence ratio, P. We have already discussed about this P when we discussed about stoichiometric principle. So fuel or equivalence if P is less than 1, it is fuel lean condition. When P is greater than 1, it is fuel rich condition. Okay, now my question to you is, will be high?
Just lean, sir. Not very, just lean, like 0.9.
Slightly lean. Any other answer? Why do you think slightly lean is going to increase the max temperature, maximum temperature?
So that is basically because if the fuel is rich in the system, so because of some heat is also expanded on like giving the place in the system after burning that sense. So the flame temperature peaks at that particular lambda.
Sir, it will ensure complete combustion of the fuels.
Slightly lean will ensure complete combustion. Okay. Does stoichiometry also ensure complete combustion, right? Does stoichiometry ensure complete combustion? It can happen with stoichiometry also, right?
Yes, sir. But yes, I've told you, sir, that basically the latent heat of evaporation of fuel will be a very minimum phenomenon at phi is equal to 0 and phi is equal to, sorry, phi is more than 1 and phi is equal to 1. Whereas phi slightly lesser than stoichiometric will have completed that phenomenon absent. That will help the flame.
No, I do not agree with that. I will talk about that when I discuss about phase of fuel and its effect, latent heat effect. That is what you are talking. Okay, so here there are more some other dominant effects. Maybe you should think about other dominant effect rather than the latent heat effect. Latent heat effect, I'm going to talk next.
Sir, so in ideal case, sir, so in ideal case, it should be when phi is equal to 1.
Phi is equal to 1. So you are saying this will increase max temperature. And the other answer is slightly lean will increase max temperature. Any other answer?
Sir, I think it might be because of a rich mixture. Reason being, the chemical kinetics would be more, and that's the reason why the temperature would be high.
So how rich you are saying? When you say rich, it is qualitative. Like the Rosen said, it's slightly lean. So what? How much of richness, fuel richness you are talking here? Because P greater than 1 can be anything, right? It can be 2, it can be 10, 5.
Understood, sir. I'm just thinking on it.
Slightly rich means 1 point
Slightly rich.
less than 2 if it is 1.4, 1.6. If it is in that range, in my opinion, it will give higher flame temperature, because more the fuel which can burn abruptly will give higher temperature.
But more the fuel, you will have incomplete combustion, right?
Yes, sir. So like maybe 1.2 or 1.4 rich. That's the reason, sir. We give at the starting we give the choke, and we slightly make the air fuel mixture little rich.
Slightly rich is perfect answer, but the value you are talking is incorrect. You are talking about very high peak value.
Slightly rich is the correct answer. There should be 1.1 around, in my opinion.
Yes, slightly rich is what is a perfect answer. That is where you will have maximum flame temperature. With the lean, too lean, the problem is, as you know, if he is less than 1, you are burning less fuel. The thermal energy release is a strong function of how much of fuel you burn, as simple as that. So when you go towards lean side, you are burning less fuel. So obviously the temperature reached is less. So that is how with the lean you are going to get lower temperature. With too rich mixture, the problem is you will have more incomplete combustion. Incomplete combustion, you know, is going to reduce the temperature reached because carbon doesn't bond to CO2, hydrogen doesn't bond to H2O. That is what is complete combustion. That is going to increase the thermal energy release. When there is an incomplete combustion, I am saying that C bonds to CO, right? Then there is a considerable drop in temperature that is reached. Although you are burning more fuel, because of incomplete combustion, the temperature reached is less because the event is not complete. Combustion event is not complete due to oxygen deficiency. So you have a problem here with rich and lean. So preferable is stoichiometry, but stoichiometry, you know, it is a chemically correct or theoretical correct proportion of fuel and air. So even after stoichiometry, there is some oxygen left. So with a slightly rich mixture, that excess oxygen available is also utilized when you have some more additional fuel than a stoichiometric proportion. Slightly rich mixture, if you have, that additional oxygen is also utilized and you will have a maximum flame temperature reached. So maximum flame temperature is reached with slightly rich mixture, closer to 1, but on the rich side, not on the lean side. Okay. So this is the effect of fuel or equivalence ratio on the maximum combustion temperature that is reached, okay, due to combustion event. Then about the phase of fuel, which you talked, the phase of the fuel also affect maximum flame temperature because we have different types of fuel. They may exist in liquid phase, they may exist in gas phase. And please note that combustion is a gas phase phenomena. When you are introducing liquid phase fuel, and our conventional fuels, gasoline and diesel, are liquid phase fuel. They exist in the liquid phase under ambient condition. Combustion is a gas phase phenomena. So how do you convert this liquid phase to gas phase?
By adding heat.
Specifying heat.
Yes, by adding heat. And what is that heat referred as?
Latent heat of vaporization.
Latent heat of vaporization. So you need latent heat of vaporization to convert liquid phase fuel into gas phase fuel in case if you are using a liquid fuel, which is what we are using, conventional fuels or liquid phase fuel. So we need to convert this into gas phase. So where from this latent heat is obtained in a combustion system, IC engine combustion system, SI and CI engine, you need latent heat because combustion is a gas phase phenomena. Where from this latent heat is obtained?
Chamber walls.
Chamber walls.
Chamber walls. How can chamber walls supply energy?
Sir, in
Yeah, in SI engine,
we
it's a
pressurize the air.
Yes. SI engine?
In CI engine, we pressurize the air fuel mixture. So by pressurizing the air, it it increases the temperature. And in case of SI engine, we provide a spark that gives a instant flame, and that increases the temperature.
No, you should have gas phase mixture available in the spark plug at the time of spark discharge. What you need is a gas phase mixture of fuel and air prepared in the ignitable range. Otherwise, whatever you do with spark discharge, combustion is not going to happen.
So basically, the latent heat of evaporation is taken
Air,
from the
surrounding
air,
air.
because air
That
is
is a
suppose
perfect answer. So latent heat of vaporization is taken from air, both in SI engine and CI engine.
that's why the intake air and temperature entering of the combustion chamber has a temperature difference.
The source is air. Okay, source is air to convert liquid phase to gas phase. Latent heat for vaporizing the fuel, liquid phase fuel, is taken only from air, both in SI engine as well as in CI engine. So when you analyze a combustion event, I will talk more about combustion analysis later on. You will see that when you analyze heat release, initially there will be a dip in the heat release, and then the heat release will start to increase, something like this. This dip in the heat release is primarily because you are absorbing heat from the system, combustion system. The heat absorption is indicated through the dip in the heat release, and then it will become positive. So there will be a change in slope when you analyze heat release. Later on, I will talk about that. When you analyze heat release, you will notice this. So the source for vaporization, liquid phase fuel vaporization, is air. Because of absorption of latent heat from air, you will have a dip in the heat release before the start of combustion event. Then it becomes positive. So when you have a liquid phase fuel, the problem is you need some heat in the beginning before the combustion event is started, because the combustion is a gas phase phenomenon. And this conversion of liquid to gas phase happens by absorbing latent heat from air. So the energy required for vaporization is taken from the system itself. Okay, this is the energy absorption. So ultimately it will reflect in the flame temperature. The flame temperature will get reduced if you have a liquid phase fuel as compared to gas phase fuel. In gas phase fuel, already you have a mixture, fuel air mixture existing in the gas phase. So there is no question of heat absorption or energy absorption when you have a gas phase fuel. So you can expect, keeping all other parameters as constant, if the fuel exists in the gas phase, you will have maximum adiabatic flame temperature. Okay, so other important information you should note down here is whenever I talk about the effect of one variable, okay, I assume that all other variables are constant. Did you understand what I am saying?
Yes, sir.
Yes, sir.
That is how you can capture the effect of any variable. Even if you do research on engine, whenever you want to establish the effect of any variable, you should keep all other variables as constant. You cannot have multivariable analysis that will make the system more complex. You cannot examine or find out what parameter influences more. Okay, when you have multivariable. So when you do a parametric analysis, you should see that only one parameter is a variable at a time, so that you can establish its effect. So here, what I mean is, if you have a liquid phase fuel, you're going to have a drop in the maximum flame temperature because some energy is absorbed in the beginning to get converted to gas phase. The other variable is external conditions imposed on the reacting system, chemically reacting system. So what are the external conditions imposed on a chemically reacting system? The system can undergo combustion event under two conditions. One is constant volume combustion. Second condition is constant pressure condition. In which case the maximum temperature will be higher?
Constant volume, sir, because there is no work involved.
So here the maximum flame temperature is going to be higher compared to constant pressure, because in a constant volume combustion system, there is no flow work. There is something called flow work. In a constant pressure system, the flow work is there because you are spending some energy to move the fuel and air into the system, and you are spending some energy to move the products from the system. So there is something called flow work. Some amount of energy is utilized for the flow work in a constant pressure system. If you have a constant volume system, there is no flow work. So the maximum temperature reached will be higher in a constant volume system because of this reason. So these are the variables. We understood that these are affecting the maximum flame temperature. This is also important to understand because we need to know what are the variables that affect the maximum combustion temperature. Now, with that understanding, we are moving ahead and we are now going to see an expression for finding adiabatic flame temperature by a law of thermodynamics. So we are considering first a constant pressure combustion case. Okay, we are going to get an estimate of adiabatic flame temperature for this constant pressure combustion. So as I said, we are applying first law of thermodynamics to a chemically reacting system to get an estimate of adiabatic flame temperature. So we are applying this first law to a chemically reacting system. When you do this, you know when you apply first law, you can write it as Q minus W is equal to delta U. This is a basic equation from where you arrived at this equation. Q is equal to delta H. Since it's a constant pressure combustion system, if you combine W and del U, you get H, enthalpy. Enthalpy is U plus PV, you know. Okay, so from this you can write it as Q and you have a subscript here R to P. This R stands for reactants and P stands for products. So this is a standard nomenclature followed to indicate that it is a chemically reacting system. Initially, the matter is in the form of reactant, fuel and air. After combustion, it is in the form of products. Okay. So Q R to P is equal to delta H R to P. This is for a constant pressure combustion system. This delta R H R to P can be written as HP minus HR. Since we are considering adiabatic flame temperature, Q will become 0. Okay, so Q will become 0 since it's adiabatic. You can write it as HP minus HR is equal to 0, meaning HP is equal to HR under adiabatic condition. So by equating enthalpy of the product and enthalpy of reactant, you will be able to get an estimate of adiabatic flame temperature. Okay, so this is an outcome of first law of thermodynamics. From that you get HP is equal to HR for a constant pressure combustion system. Now I need to explore more. I need to expand and find what is HP, what is HR. What is HP? HP stands for total enthalpy of the product. So when I say total enthalpy of the product, or reactant, this has two components. Enthalpy has two components here. What are the two components you can think of? In a chemically reacting system, H has two components. What are they?
One is to break the bonds and the other is to add another heat to the system.
Exactly. So one is to break the bond. This is enthalpy associated with the formation of a compound from its element, and other one is called sensible enthalpy. This is an enthalpy associated with temperature. So this is enthalpy associated with chemical bond. And the sensible enthalpy is enthalpy associated with temperature. So this comes from the type of compound we have in the fuel. Accordingly, the enthalpy of formation is going to be different. So we said that we have a hydrocarbon fuel. In the first chapter, we discussed about that. Diesel and gasoline are mixtures of hydrocarbon, multi-component mixtures of hydrocarbon. So you have different hydrocarbon with different molecular structure, right? According to the molecular structure, the enthalpy of formation is going to be different. So this enthalpy is associated with a chemical bond. That will decide how the hydrogen and carbon get connected, and based on that, you will have thermal energy associated with the formation of the compound. This is one element. The second element is associated with the temperature of before undergoing the combustion event. It can be existing at any pressure and temperature conditions, right? So the temperature, initial temperature, is going to affect the final combustion product, as I said in the beginning. So it can be any temperature. Now to account for that, we are considering the sensible enthalpy, wherein this is the enthalpy associated with the temperature of the reactant. So this H has two components, okay? And we are expanding this enthalpy of products and reactant based on whatever we discussed now. So this HR is enthalpy of reactant. This can be written as summation I, R. I is any species in the reactant, right? Summation of number of moles of species I multiplied by delta HFI with a circular symbol here, and then there is a bar here. The circular symbol stands for standard condition. So we always compute enthalpy with reference to a standard condition. What is that standard condition? Standard condition is mentioned here, 1 atmosphere and 25 degrees Celsius temperature. Okay, that is what is delta HFI. And this bar symbol stands for, this is a molar basis, not mass basis. This is mole based enthalpy. So to indicate that, you use a bar above delta HF. Okay. So this first element, as I discussed, is the first component of total enthalpy, which is associated with chemical bond, which is nothing but enthalpy of formation. That is what it indicates. That is delta HF I, enthalpy of formation of species I at standard condition, which is 1 atmosphere and 25 degrees Celsius. And this is on mole basis. That is what this bar symbol indicates. Okay. Plus enthalpy associated with temperature, which is sensible enthalpy. Now, enthalpy associated with temperature can be written as CPT. Right? This is how you express enthalpy associated with temperature. H is equal to CPT. That is what I have done here. This is Cp on molar basis, okay, with a bar, Cp with a bar. This is on molar basis of species I, specific heat capacity of species I, right, on molar basis. And what you have here is dT and Cpi as a function of T. And it is coming under integral symbol from T naught to Ti. Can anyone tell me why I have expressed this Cp dt in the integral form rather than a finite form, H is equal to CPT?
Because temperature will change while the progress of combustion is happening.
So Cp, what about Cp with respect to temperature?
That will remain constant, sir, that you have told earlier.
Cp will remain constant with temperature, specific heat?
That's what you have told in the beginning of the course, sir. I'm sorry.
The beginning of the course. I don't remember. I said Cp is always constant. Cp is a variable with the temperature actually.
Okay.
So that is why you
Yes,
have
sir. Cp will vary with the...
Yeah, go
Yes,
ahead.
yes, yes. Please. Yes, sir. Cp will be a variable with reference to temperature. So
Yes.
we want to take the holistic picture of the entire volume. So that is the reason we are integrating it.
Yeah, Cp is a variable with temperature. Cp is a function of temperature. Okay, that's why you have Cp coming inside integral form. Okay, this integral form stands for Cp is a variable. That's why you have indicated that Cpi T, meaning that Cpi is a function of temperature. Okay, so specific heat capacity is a function of temperature. With variation in temperature, you will have a variation in Cp value. So if you look at standard tables, so you will see that Cp will vary with temperature. At a lower temperature range, almost the trend is linear, but at a higher temperature, the trend is almost non-linear. That is how Cp varies with temperature. So Cp is a strong function of temperature. It varies with temperature. So in order to integrate this equation, you have to express Cp in terms of temperature value. Then you will be able to integrate it and get the Cp value, okay, over the temperature range encountered in the combustion system. So it is going to be variable. It's a function of temperature. Okay, that is what it says. Now you have two components. The first one is enthalpy of formation. Second one is sensible enthalpy expressed in terms of Cp, which is a variable with respect to temperature. This is for the reactant. Then for the product, Hp is equal to same equation you can write. Summation of I comma P. Ni is number of moles of species I. You have two components. One is enthalpy of formation. Second one is sensible enthalpy expressed in terms of Cp dt. Okay, because Cp is a function of temperature. So when you look at the temperature range of the integral for reactant, it is from T naught to Ti. For the product, it is from T naught. T naught is the temperature under standard condition, which is 25 degrees Celsius. Ti can be anything. Ti cannot be 25, right? Exactly. So that's why we are accounting that through sensible enthalpy for reactant. For product, definitely the temperature is adiabatic flame temperature, which is much higher than the T naught value. So you are integrating it from T naught to T adiabatic, which is adiabatic flame temperature. Okay, and so you are equating HR and HP to get the value of adiabatic flame temperature. In this equation, the only unknown is adiabatic flame temperature. You will get Cp from standard table. Delta HF for various species are available from standard thermodynamic table. Cp and HF are available. Only unknown is T with a subscript AD, which stands for adiabatic flame temperature. Okay, so by equating this HR and HP, you will be able to get this unknown. So only unknown here is adiabatic flame temperature that you can get from the first law equation, which is HR is equal to HP. Sorry. So for a constant volume combustion, yeah.
Sir, for reactants, is it like considering the gaseous form, or is it like it is including both liquid and gaseous form?
It's gaseous form. So whatever we are talking here is in the gaseous form.
Okay, sir.
The phase change is accounted through latent heat. Okay.
Okay, sir.
Now for a constant volume combustion, you can write first law equation. Again, it's a chemically reacting system. You are indicating that with this symbol R to P. It's a chemically reacting system. By first law equation, you can write it as Q minus W with the subscript R to P is equal to delta U R to P. Since volume is constant, there is no displacement work. W will become 0. You know W is equal to integral P dV. There is no dV term here because volume is constant. So W becomes 0 here. And Q will also be 0 because we are considering adiabatic system. There is no heat interaction between the system and surrounding. So first law equation will be reduced to delta U R to P is equal to 0 because Q is 0, W is 0. From that you can write it as UR is equal to UP. So here for constant volume system, we are equating internal energy, total internal energy of reactant and total internal energy of product to get the adiabatic flame temperature. Internal energy is very difficult to get from any standard table, but you can always express internal energy in terms of total enthalpy. So you know this equation, H is equal to U plus PV. So you can express this U in terms of H and PV. Okay, and this PV can be expressed in terms of N R bar T. This is the equation of state. There are different forms of equation of state. I prefer to use this form here because we are writing any combustion equation on mole basis. As I said in the beginning, PV equal to N R bar T is what will be the equation of state we will be using here because we are writing combustion equation on molar basis. So if you consider UR, you can write it as HR minus PR VR. UP can be written as HP minus P with a subscript T, V with a subscript P. This P stands for product, R stands for reactant. Now again, HR minus PR VR, this PR VR can be expressed in terms of N R bar T from the equation of state. What is this R bar? R bar is, what is R bar in the equation of state?
Ideal gas constant.
8.314.
Yes, this is universal gas constant. Gas constant will be written as R simply. So this is gas constant. R with the bar is universal gas constant. It is a constant value, 8.314 is its value. Kilojoule per kilomole Kelvin. This is the value of universal gas constant. Okay, so we can write this PR VR as N with a subscript R, R bar Ti. So R bar is constant, Ti is initial temperature for the reactant. Similarly, on the product side, you can write it as HP minus NP, R bar T with a subscript AD. This is the adiabatic flame temperature. So we already know that we can get this HR and HP from standard table. Now here again, the unknown is T adiabatic, which is adiabatic flame temperature. By equating UR with UP, you will be able to get an estimate of adiabatic flame temperature for a constant volume combustion system. So that is how you get an estimate of adiabatic flame temperature for a constant volume and constant pressure combustion system. Okay, by applying first law of thermodynamics. So what we have discussed now is application of first law of thermodynamics to study combustion. We derived two parameters. One is heating value, which is an estimate of thermal energy released during combustion. Second useful parameter is adiabatic flame temperature, which provides an estimate of what is the theoretical maximum temperature reached during the combustion. So we have discussed how we can apply first law of thermodynamics to get these two useful parameters. Next, moving ahead, we are going to see how we can use second law of thermodynamics to get a condition for chemical equilibrium. So earlier we have discussed that this stoichiometric principle provides you combustion product with the maximum number of product composition being 4, because you have only 4 atom balance equation, right? So you cannot get more complex product information by applying this stoichiometric principle. Considering that, we can use chemical equilibrium concept to form additional equations so that you can get an estimate of product composition. Please remember that as a resultant of combustion, various products are formed. We need to know about the composition of the product. What do you mean by composition of the product? Number of moles of various species which are formed. When you do experimental measurement, you know you use an emission analyzer to get an estimate of the product composition, right, from the combustion, even because some of them are pollutant. So with stoichiometry, you can get only minimal number of products. That's why we are moving ahead. We are going to now see how we can apply a concept called chemical equilibrium so that we can get more number of products. Okay, we can get the composition of more number of products by doing this. Okay, so we are going to see what this chemical equilibrium is, what kind of how useful this chemical equilibrium concept is in terms of estimating the product composition. That's what we are going to see here. So this is, as I said, this concept is helpful to determine the composition of the combustion product. We need to know about the composition of the combustion product because some of them are pollutants. Can you please mute your mic? So this concept is useful to get the composition of combustion product that cannot be provided by stoichiometric principle alone. Okay, so we are going to discuss about this chemical equilibrium concept. You know, composition of the combustion product depends on two parameters. One is fuel air equivalence ratio. The other one is temperature. Both temperature and equivalence ratio influences composition of the combustion product. Let us see how. I have already discussed about this when I discussed about stoichiometric principle. Suppose if P is equal to 1, this is called stoichiometric condition. Under stoichiometric condition, the major combustion products, note down the word major combustion product. In the real engine also, these are the major combustion product. Apart from this, there are several other minor products. We are ignoring all those here. Okay. So when P is equal to 1 under stoichiometric condition, you have only 3 major combustion products. One is CO2, carbon bonds to CO2, hydrogen in the fuel bonds to H2O, and then N2. Here N2 is based on the assumption that the temperatures are less. Nitrogen in the air is coming out as it is. But in a real engine, as you know, nitrogen bonds oxidizes to NO and NO2, which is what is NOx. So here we are considering that the temperatures are less and nitrogen comes out as it is. Nevertheless, in a real engine also, these 3 are the major species, major combustion product in an actual IC engine. So when Phi is equal to 1, you have only 3 major products that comes out of the IC engine. Suppose if Phi is greater than 1, what is Phi greater than 1?
Rich mixture.
Rich mixture. So this is stoichiometric mixture. This is fuel rich mixture. So when you have a fuel rich mixture undergoing combustion, what are the combustion products that you get? The combustion product that you get are you will have CO2, you will have H2O, you will have N2. This three. Apart from this, you could see the two other species. What are the species? CO. You know, CO is a product of incomplete combustion. You are talking about fuel-rich combustion, meaning that oxygen is less. So oxygen deficiency is there. Due to oxygen deficiency, carbon bonds to CO also. Apart from bonding to CO2, it also produces CO. This is a product of incomplete combustion. Similarly, the hydrogen in the fuel bonds to H2. Not only H2O, H2O is complete combustion of hydrogen. If there is incomplete combustion, then it releases this unbound product, H2. Okay, so you will have the CO and H2. These are unburned product when you have a fuel-rich combustion. Now, how many products are there? How many product?
5.
You have 5 species. Now let us talk about the other possible condition, Phi less than 1. When Phi less than 1, what is that called as? It is a fuel lean combustion. When I say fuel lean, I have more oxygen. Okay, this is what I mean by fuel lean. If you have more oxygen, you look at the combustion products, you will have CO2, major product, H2O, major product, N2, this 3, as you could observe in stoichiometric condition. Apart from this, you have one more added. Oxygen is added because you are doing fuel lean combustion. There is more air, excess air that appear in the combustion product. Okay, oxygen will also be a major species if you have a fuel lean combustion. Now, how many products are there? How many species are there? 4. Okay, so you have 4 species here when P is less than 1 under fuel lean combustion. Okay, so how many equations you can form from stoichiometry? So you have 4 unknowns here. How many equations you can form from stoichiometric principle?
4 equations.
4 equations, because you have 4 atoms. You are doing an atom balance. You can form at the most 4 equations. What are the atoms we are talking? In the fuel, you have carbon and hydrogen. In the air, you have oxygen and nitrogen. So you have only 4 atoms. With that, you can form at the most 4 equations. So these 4 unknowns, whatever you are seeing here with fuel lean combustion, can be obtained by doing stoichiometric principle. Okay, by applying stoichiometric principle, you can get the product information, product composition. Okay, this is what is the case when the temperatures are less. I have given a threshold temperature value. When temperature value is around 1250, there are only 4 unknown. So 4 atom balance based equations are sufficient to get the information about the number of moles of these 4 species. This is what I mean by product composition. Suppose if the temperature is above 1250, then some other reactions are going to happen. Those reactions are called dissociation reaction. Dissociation reactions are basically endothermic reaction, meaning these reactions absorb thermal energy. Combustion is exothermic. The exothermic reaction will release thermal energy. Endothermic reaction will absorb thermal energy. Okay, so at higher temperature, dissociation reactions happen by absorbing thermal energy. CO2, H2O are stable species. When the temperature increases, the stable species will start to dissociate. Okay, you could see here that this is a typical CO2 dissociation reaction. Carbon dioxide dissociate and form CO and oxygen. Hydrogen, H2O dissociate and form hydrogen and oxygen. This is H2O dissociation. These 2 are the major dissociation reactions in IC engine combustion. So this is going to happen in a real engine also, real engine combustion also. These are the major dissociation reaction. Now what you could observe here, CO2 as such is stable, but when the temperature increases above 1250, you know in IC engine combustion, these temperatures are very well reached. You will reach well above 1250. So what is happening because of that? CO2 start to dissociate and form CO. H2O is stable at low temperature. At this temperature range, it is dissociating and forming H2. What we have discussed earlier, CO and H2 are available in fuel-rich combustion. Please note here that we have discussed just now that only in fuel-rich combustion you can expect CO and H2 because these are the products of incomplete combustion. But what we are seeing here, even with the fuel-lean combustion, even with excess oxygen, you will have this incomplete combustion product, CO and H2. Suppose the temperature increase above 1250. Even with lean combustion, fuel lean combustion, CO and H2 appear in the combustion product under lean condition, provided the temperatures are 1250. Now, how many unknowns are there in the product? How many species are there? You have CO2, H2O, O2, N2, standard species. Because of dissociation, CO and H2 are also added. Now, how many are there? You have 6 unknowns. Okay, 6 unknowns you have at high temperature. Okay, so 4 atom balance equations are insufficient to estimate the composition of combustion product. You cannot apply stoichiometric principle and get the information about the product composition at high temperature. This is where chemical equilibrium concept is useful. It provides reasonable approximation to compute composition of combustion product at high temperature. Okay, so at higher temperature, you are going to get more number of species, and you can have an estimate of that product composition if you have chemical equilibrium concept applied. Okay, by applying this concept, we are going to get the number of moles of these many species, which is not possible with stoichiometric principle. It's time up. I stop here. If you have any questions, I can take your questions.
Sir, why NOx was not considered in fuel in conditions?
NOx is not considered. As I said, the temperatures are less. NOx will form at well above 2000 Kelvin.
Okay.
This is an assumption actually. This is an assumption. These are the major product. NOx will be there with the ppm level. You know, when you measure NOx, you know that it is in ppm level, right? Parts per million, 1 by 10 power 6. We are ignoring all those minor species here in this analysis.
Okay, sir. Thank you, sir.
Thank you. Any question?
Sir, am I audible?
Yeah, yes.
So for phi greater than 1, we are directly getting CO and H2. So in that case, what is the temperature in that condition?
So that is at any temperature you are going to get CO and H2. What I have demonstrated here with the lean combustion is when the temperatures are less, you will have less number of species. When the temperatures are more, even with lean combustion, you are going to get CO and H2. That is what I have provided here. So basically what I want to convey here is the number of species in the product, major species in the products are going to increase when the temperature of the combustion system increases.
Noted, sir. It will be more or less greater than 1250 Kelvin, correct?
Yes. So you will have more species. You cannot find the product composition by applying stoichiometric principle alone. Okay.
So this
Yuvraj just raised that.
This will be valid for.
Just only one thing only. I joined at 6:03 p.m. sir. So I think you have marked me up.
It's not clearly audible. Whatever you said, can you say it again?
Sir, you have marked me absent. I joined at 6:03 p.m. actually. Just 1 minute, 3 minutes late. So.
Okay. So I have. Okay. So you are talking about attendance. Fine. Okay, I have considered. Yeah.
Thank you, sir.
Yeah.
So
fine.
my question was that the 6 species for phi less than 1 and temperature more than 1250 Kelvin. That will be holding true for even phi more than 1, right, sir?
For phi more than 1, even the normal number of species itself are high.
Okay, that was 5.
Normal in the sense at any temperature.
Yes, it was 5 actually, right?
Yeah, 5. So you cannot find the product composition with the stoichiometric principle alone, because at the most you can form only 4 equations, meaning you can find only 4 unknowns.
So whenever the product number goes more than 4, we have to apply the
chemical equilibrium concept.
Right.
So you can. So what I am going to show how it will be helpful by taking a case study. What is generally done is you will apply stoichiometric principle, get 4 equations, then form additional equation by applying chemical equilibrium principle. Those additional equations will be helpful in solving and finding the product composition.
Okay, sir. Thank you.
Okay, fine. Okay, so it's time up. I stop here. I will meet you tomorrow at 6 o'clock. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.